Thank you for coming to our seminar today. I'm Richard Corkish from the School of Photovoltaics and Renewable Energy Engineering, and our speaker and guest today is Professor Vasilis Fthenakis from Columbia University. So Vasilis was the founding director of the Centre of Life Cycle Analysis, and he is still the director. He's also adjunct professor, Department of Earth and Environmental Engineering and Department of Electrical Engineering at Columbia University, and Distinguished Scientist Emeritus at Brookhaven National Labs. Vasilis is internationally recognised for his leading work in the energy and environment nexus and renewable energy grid integration, with a focus on developing methodologies, models and tools to analyse cleaner energy alternatives. He has been a pioneer in studying the environmental impact, resource availability and recycling of photovoltaics, accelerating their commercial introduction around the world, or adoption around the world. More recently, he broadened his centre's research to explore solar-enabled water desalination and green hydrogen production. He's a fellow of the American Institute of Chemical Engineers, a fellow of the Institute of Electrical and Electronic Engineers, and a recipient of several honours and awards, including the 2022 Carl Bohr Solar Energy Medal for Merit for distinguished contributions to the quest for sustainable energy. Vasilis, thank you very much for visiting us and giving this seminar, and please go ahead.
Thank you, Richard. The pleasure is mine. I'm both honored and humbled to be at the UNSW, the leading institution in the world on crystalline silicon R&D, in the company of Martin Green, of Richard Corkish, and other distinguished scholars here. So I'm going to give you some insights and perspectives on work that I have been doing initially at Brookhaven National Laboratory and following up at Columbia University on sustainability over the last 4 decades. And I will start with a reference framework for sustainability as I see it along 3 basic dimensions with well quantifiable metrics like cost and resource availability and environmental impact. By cost we mean affordability, not only for the rich Australians and Americans and Europeans, but also for the developing world that doesn't have access to electricity. With environmental impact, we're talking about local, regional, and global impacts in a comparable context, because there can be no zero impacts, really. So we compare with other technologies. And with resource availability, we're talking about materials and the land and water, again, in a comparable context, but also in an intergenerational, actually, context, looking for the following generations, for us not to deplete resources that are finite and have actually create issues with the other, with the follow-up generations, children and grandchildren. So I look at this actually for perhaps decades period as initial kind of infancy, then junior, and then adult, and I will just highlight my professional actually path during those years. The work started at Brookhaven National Lab in the mid-80s, and then we were looking under the auspice of the Department of Energy, we were looking to help, for the most part, environmental health and safety in startups and laboratories. So to help them to maintain safe facilities, safe labs, safe startups. And the cost issue was not really a major one, because the markets were niche markets. We were taking off-the-grid small systems in developing countries, and some architectural designs, kind of statement type of designs like the ESCN in the Netherlands. Following up in 2000, perhaps 1998 to 2005, I call it a junior stage, that when we had big markets started it with incentives, subsidies in Japan, then in Germany with RPS, early 2000, then the big markets and profitable markets started it, and the cost issue had to do with perhaps competition in peak shaving markets. And as you know, peak electricity is more expensive than base electricity. So photovoltaics didn't have to get to very, very low prices to be competitive for peak shaving markets. for environmental impact, we actually working with others and organizations, the DOE and NSF and so on, to develop standards for the industry, how to maintain environmentally friendly facilities. And then we reached to what I call adult stage, where we are now. It's the longest stage, where the affordability issue became actually affordability in a competitive world. Prices that are lower than the prices of electricity from coal, natural gas, and nuclear, and so on. The life cycle impacts, it included investigations of the potential impact on solar farms, big solar farms, potential actually on the ground. And the material availability became a real issue. Because of some technologies, you have minor elements from the production of base elements like tellurium for production of copper, indium for the production of zinc, and you have silver and so on. And those are finite resources with relative, actually low, perhaps, production at those, in those years. Also, we started looking more intensely on energy use to answer questions about the energy use on energy investment, energy return on energy investment, and land use. Now, the cost issue has been actually addressed. As you know, solar electricity, at least from utility size, utility plants, is the least expensive electricity now. Solar and wind. In the United States, for new plants, solar plants, actually, they're the least expensive ones. Even for, starting actually from 2021, even less expensive than wind for any new plants. And they price down now to about $35 per megawatt hour. Is actually almost as low as price of electricity from fully depreciated nuclear and coal power plants, and a lot cheaper than new plants with any fossil and nuclear. So the cost issue has been addressed already. Now, what about other issues that have to do with resources and environmental impact? There are questions there. Some actually reflect real issues. A lot reflect perceptions, like photovoltaic power plants can pollute the environment, that PV growth is constrained by material availability. That's a real issue. I'm going to discuss that. Energy return on energy investment is too low. That's a perception for some. It's not an issue. That PV deployment uses too much land, again, a perception, depending on how you look at it. And that photovoltaic power plants create a heat island effect, a real issue that we investigated. So let's start with some of the perceptions, perhaps. Over the years, we actually developed a bibliography with many journal publications, conference presentations and publications, and magazine publications, trying to proactively answer all these questions. So we took the extra step, as scientists should do, to disseminate as effectively and as broadly we could the results of our research. High impact journals, but also magazines and even newspapers, and a lot of interviews those years. Actually, I think a leading study that he combined the three metrics, the resources and impact and cost. It was published in Scientific American in 2008 and was translated in 8 languages. So everything has been fine. And now currently, photovoltaics, as we know, lead the energy transition. It's the least expensive new energy production, new energy actually generation, at least in some areas. But still, there is a debate. You couldn't imagine that. So what you see here is an article that was published late in 2021 in Energies, where the authors Siebert and Rees actually they contested the inherent, as we know it, actually nature of photovoltaics as being renewable. So as you can see, I don't know if you can read some of these actually words. They call solar as so-called renewable energy. The espoused technologies are not renewable, they were claiming. From mining to installation is fossil energy intensive. Producing them, particularly mining their metals and discarding their waste, entails egregious social injustices and significant ecological degradation. And they had about actually 70 citations, most irrelevant, but they also cited a few anti-solar articles in the literature, a few of those. Now, this obviously was erroneous, and we had to address it. So we protested to the editor-in-chief, and he invited a rebuttal and promised accelerated publication, and we did actually rebuttal with 16 other co-authors, where we pointed out to the many flaws of the Siebert and Rees paper, and what they've done, we put it out, they have selectively picked up maybe 5 or 6 anti-solar articles in the literature, and they didn't mention hundreds and hundreds of articles that they were given. They were actually solutions on what was the potential problem there. Now, this actually quick and dynamic response had lasting effects. The editor-in-chief apologized for actually accepting the original manuscript in the first place, and I think we had some lasting effects because they put some additional safeguards there in the peer review. Because actually, essentially what we've done is we chastise the journal for not having inadequate peer review, and they admit it, and they put safeguards there. Now, some real solutions now. I mean, some real problems and real solutions. Supply for minor elements like tellurium, indium, germanium, gallium, silver. We feel that actually there are different solutions for tellurium. For example, the supply can increase. I will give you a few highlights of what I believe is the case there. For indium and silver, the demand can be reduced. I don't think the supply can increase a lot there because there are very mature, actually, production markets there. And as you know, silver can be also displaced with copper and aluminum. So let me give you highlights of the stories. We don't know much about tellurium production. We don't know exactly what is tellurium production today. I think it's about between 600 and 800 actually metric tons per year. But we know a lot about the copper production. Copper has been actually followed for many years, and we know that it's about 3% increase on the primary production of copper over the years, with a little actually break during the COVID years. The projections following different ICPP actually scenarios with different assumptions on population densities and living standards and so on, they show that copper will probably actually is going to peak. The primary production of copper is probably going to peak early in the second actually half of the century. Now, tellurium is a byproduct of copper production. Most of what we have now in the market is from copper sulfide ores, byproduct of the copper production. So we feel that it's going to follow the same trend, really. So let's see what happens actually, how it's produced in copper circuits. Down here is produced actually as a byproduct from the refining of copper with anode slimes. So if we get about 50% actually of tellurium that it is in those slimes. So from 100 tons in the slimes, we get about 50. Now, these 100 tons of slimes come from about 500,000 metric tons of copper sulfides, assuming a 0.5% actually copper in the ore. And if we get what is the range of tellurium, about 1.5 ppm to 1.9 ppm, it corresponds to about 180 to 260 metric tons of tellurium. I want you to note here that about half of this is actually unused. It ended in tailings and potentially can be used. Okay, if there is a market and the price, but currently it's not used. So we get in here, we have other losses in the air pollution control equipment that could perhaps be recovered and so on. But even without this additional recovery, we're talking about with 50% recovery at the end, we can have, if all the production of copper actually co-produces tellurium, we can have 2,000 metric tons. But I think maybe less than a half of this can do that because copper oxide does not really include the tellurium, copper sulfide does. But anyway, I think that now we are about 600 to 800 metric tons. And again, following the scenarios of copper production that I showed before, we expect a peak at about 2060, 2070. And I have actually bracketed this in low and high, depending on the scenarios and also depending on assumptions about the increased recovery from anode slimes. It's noted that selenium is recovered by about 80%. And so perhaps, and gold and platinum actually about 95, 98%. So the 45 to 50% recovery rate could increase. But anyway, we're going to have a peak at this point unless we do recycle. Okay? With recycling, actually, you can have a very important secondary resource of tellurium in this case. And it is proven. I mean, you can recover it. There is technology. A major company in this production for solar, it recycles, they scrap and so on. And you can have 95% recovery actually of tellurium there in the commercial scales. So then the peak is actually shifted to the next century. By then we may have fusion, or of course we have so many other technologies that we don't need tellurium any longer. With this actually primary and secondary resources giving a high perhaps ceiling on what could be the production of cadmium telluride, we still have these projections. We can make these projections. Again, optimistic, most likely conservative, correspond to different efficiency, different film thickness assumptions according to different scenarios of production. We're here, I think this company that is the only big company in the world that produces cadmium telluride is actually close to 16 gigawatt now, with a new production about 7 gigawatt in India. So we're about here, we're along the conservative one. But not far of what we projected about 10 years ago. Now, the value of recycling becomes apparent here, because with recycling you have a secondary resource of tellurium. The same corresponds to the other elements from other products, indium and so on, germanium. You have a secondary resource. You increase the availability and the potential of these technologies, and having a secondary resource also relieves the pressure on the prices. It addresses the cost, and it avoids disposal in landfills. So by far it actually improves the environmental impact. And also you save energy in addition to saving materials. So that also reduces the environmental impact. Okay, so recycling technology, again, it is developed. You can see here a schematic of technology we developed at Brookhaven National Lab several years ago, starting with module fragments in the hydrometallurgical operation, using something inexpensive, dilute sulfuric acid, in this case about 0.5, 0.7 only molar, and peroxide. Then we leach the metals and the semiconductor elements. We leave glass that we still need to make it cleaner to get it back into float glass. And this is a project actually that I'm working now. We started working with Pablo Diaz companies from the UNSW, actually originated technology, to have clean glass going back into float glass or rolled glass for silicon modules. But here the leachate that includes the metals and semiconductor goes through a series of ion exchange columns. The first will retain copper, the second will retain cadmium. At the end you have a leachate rich in tellurium, precipitates as tellurium dioxide. You rinse the ion exchange columns and you get from the first copper, from the second cadmium. You have to go over purification if it's not really 6 nines and the formation of cadmium telluride. This we actually found that it could be done at 1 cent per watt years back. Today it could be even less because you have more watts actually per module. Now, the indium story is a little different. It's actually substantially different. One, that the supply is already mature. We don't expect to have any sources actually or any higher material recovery in indium. And two, there is a lot of competition on indium from thin film displays and all of this, even the small cell phones and so on. There is a lot of competition. The CIGS technology that cannot go away from indium. If you use an indium in ITO, you could substitute indium tin oxide with fluorine tin oxide, for example. But for CIGS, they are actually stuck with indium. So there we have some numbers here from a thin film partnership. That's about the current production is about 900 metric tons per year, and they think that you can use 35% of that. And by the current production in solar, actually frontier is about, it uses 2 micron CIGS, and that corresponds to about 15.5 if you don't have big losses of metric tons per gigawatt. But if they can produce only a half a millimeter, about 400 to 500 nanometers, actually layers. Obviously, you can get a lot more production for the same amount, like 80 to 100 gigawatt per year. And actually, the optical efficiency of this material is very high. So you can get down to actually to a fraction of a millimeter, and it has been done in the lab. So this is how the industry is looking at the actually supply and the demand to get into thinner layers. And also there are in the lab there are actually prototypes that they use less indium and less silver together. So for example, Maxwell reported 25.6% efficiency for nanocrystalline heterojunction, using 50% less indium than what is the conventional technology, and using even a lot less silver by just having copper grid wires that reduce silver. Also, Longi has produced, at least in the lab, this type of cells that they use almost no indium. Now, silver. Silver, we're talking about replacement because, again, silver is very expensive and is limited, and I think already the market uses about 20% of the silver production as is, I think. So there are a lot of R&D on actually replacing silver with aluminum or copper. As you know, you have an issue with actually the contacts there if they stick so well and so on. But there is a lot of research that's going on, and even Australian startup like SunDrive, it actually broadcasted that they can go completely silver-free in silicon heterojunction by using probably copper and aluminum. And Georgia Tech, Jitrohagi, for example, that Martin knows very well, is actually trying to do this now, a project from Seto and others as well. But until actually it's replaced, silver can and should be recycled. Because actually with a current vintage of crystalline silicon, the silver recovery gives the highest revenue. So if you don't have silver, then you have a catch-22 situation. If you don't have silver, then recycling becomes more problematic because you don't have the value from silver. Okay, now with resource availability, we're talking about not only materials, land, for example, and I wanted to show this time after time because it's a myth that really photovoltaics use a lot of land. Yes, they do for the deployment or for the plant, but if you look at the whole life cycle and include the mining, the land for mining, coal uses in the United States more land than solar. Because of surface mining, that takes a lot of land. About 75% of coal in the US is from surface mining. And this actually comparison is based on only 12% efficient solar cells. With 20% efficient photovoltaics, these numbers obviously much lower, the land use of coal. And the numbers of coal are based on a lot of historical data, actual numbers, not projections. Historical data, we know the mines, how long they lasted, to what they produce, and so on. We know that many studies from Oak Ridge National Lab and Dartmouth National Lab. And also, the use of land is environmentally friendly. It's not like coal that damages the mountains, cut completely out, and you have the sludge there that it could actually leach out and so on. And you have the issues with the mining, with the miners' actually health and so on. Environmentally friendly. It does not really alter the land, okay? And it can be also dual use. There could be, with big solar farms, an impact on the ecosystem, but the industry is doing the best to avoid this. And I worked with SunPower, crystalline silicon, as you know, actually a leader in efficiency, and First Solar on cadmium telluride. For big solar farms, we're talking about 550 megawatt, and the 750 actually the big one for SunPower. For them, working to avoid sensitive areas, minimize impact on the ground, and maintain and improve vegetation. And a lot of biodiversity studies in the Southwest, in the Mojave, in the Sonora Desert, and we know more on biodiversity of different species now from these studies that before the solar farms were constructed there. Heat island effect, yes, I have 20% actually photon to electron conversion efficiency, 80% is heat. It increases the temperature locally, and we did detailed CFD studies using data with actual temperature measurements on the modules on the ground, above the ground, from 80 megawatt photovoltaic plant in Ontario, Canada. And we saw that this temperature increase dissipates with elevation and distance, and at night it cools down. So it's not a permanent, sustainable heat island effect. Yes, higher temperature, 5, 6 could be of degrees Celsius during the day, but at night it cools, and with distance about 100 meters it dissipates to the ambient. Also, when we're talking about resource availability, we have to, again, dual use of land in areas where you have good soil and you have perhaps very intense sun, having some shade from what are called agrivoltaics. It could even improve the crop production, and definitely it gives additional income to the farmers. You could have ecological, actually, services like pollinator solar farms, and you have additional actually benefits there. In areas where you have dense populations and big actually bodies of water, you can have floating photovoltaics. And in locations where you have wind and solar resources together, you can have actually both of those, and you have very good complementarity. You have wind at night when you don't have any solar. You can have more wind in the winter when you have less solar. So a combination of solar and wind makes a lot of sense. Now, the environmental impact is, as you know, actually addressed under the framework of life cycle analysis or assessment, looking into all the stages of the life, from the extraction of the materials, the quartz that goes into silicon, the metals that get into the cells and the balance of systems from the ground, refining of those elements, metals, silicon, the different other semiconductors, the manufacture of the cells, manufacture of the modules, installation, operation, and end-of-life decommissioning, if there is recycling or actually disposal. And we have metrics like energy payback times, greenhouse gas emissions, toxic emissions, many eutrophication, acidification potential, ecotoxicity potential, human toxicity potential. There are many metrics there, but I'm going really to touch of the most important, that is probably greenhouse gas emissions, even the cumulative energy demand. The energy usage typically defines the impact. The less energy actually you use, because today most of the energy is actually fossil fuel dominated, the more energy you use, the higher the impacts typically. So there are a lot of data in databases about the environmental impact of copper, aluminum, glass, and so on, different metals, silicon, typically for normal operation, but we didn't have data for potential accidental actually events. And in the case of cadmium telluride, because cadmium is toxic, there was a high interest in looking into what could be the potential, what could be the emissions if you have fires, and those actually engulf cadmium telluride photovoltaics. So to answer this, we had modules from the company, and they were cutting into pieces, and we were actually heating them according to protocols by the American Society of Testing Materials for testing materials like clothing and so on under fire, up to 2.5 hours to about 1100 degrees Celsius. So we cover all the flame temperature range that you expect in residential fires. And we looked into different types, we used different types of analysis, from thermogravimetric type of analysis, and we had scrubbers, actually 2 scrubbers in series, nitric acid, to make sure that the second scrubber has 0 actually elements there, so that the first one captures everything. For analyzing cadmium and tellurium emissions, and X-ray fluorescence microspectroscopy using the X-ray big machine at Brookhaven National Lab. And what we saw there is that actually we have a small loss of cadmium, as was quantified with the scrubber and the ICP analysis of the scrubber liquids. What we see is that actually this happened before the glasses fused together. So what you can see here is a cross-section of the module, talking about 3.2 millimeters of glass at the top, 3 at the bottom, and in the center you have everything else. So it's the EVA, is the thicker layer there, and you have the metals, and you have the cadmium telluride, the cadmium sulfide layers here in the center. And the fluorescent analysis, as you know, actually is a photon that actually activates, ionizes the atom, and then you have the hole that dissipates at a certain certain intensity and certain energy wavelength. And actually cadmium, it emits at about, I think, 23 kilo electrovolts. So you have the signature of what is emitted of the atom that it actually decays from the ionized stage, and you have the intensity of this peak, it gives concentration. So here is actually about 45,000 counts. This is a concentration, and this is the signature of cadmium here in the center. This is zirconium, that's a precursor, that's actually an element in glass. So this is before it's heated. Now, when it's heated, this is 760 degrees Celsius. It is above the softening point, but below the melting point. So you can see that the glass, it took the shape of the semi-cylindrical container. And we have the same signature here, about 50,000 counts as before, showing that cadmium is, this is just a verification that cadmium is there. I mean, what is emitted, we measure from the ICP analysis of the liquid actually in the acidic liquid in the scrubber. But it's obvious that what happens is that the losses happen before the two glasses fuse together. You can see an opening here. The black is the decomposition products of EVA that it burns at those temperatures. And you have some pressure, actually vapor pressure of cadmium at 760, not high, but you have a few torrs there. So some cadmium, it has actually has been a vapor and it went out with the byproducts of the combustion. And we have the same. The ICP analysis shows not higher losses of cadmium when we get to 1,000 degrees. Still we see the signature there, cadmium is there. Not higher when we get to even 1,100. Not more than 0.5%, 0.5% plus or minus 0.05 in all those. So it's obvious that actually the only mechanism for the cadmium to come out is before the two glasses actually fuse together. And this has really impact. And we guide the industry not to change that. At some point, the company wanted really to consider replacing the back glass with cheaper Tedlar, cheaper polymeric materials. We advise them very strongly against doing that because then cadmium won't actually be sequestered. So all the emissions in the life, you have most of the emissions of cadmium during purification and production of cadmium telluride. All of those, if they're normalized per gigawatt hour of production, and this corresponds, I think, to about 12% efficient. Now we have 18.3% efficient, so the numbers are better. There are only 0.02 actually grams per gigawatt hour, and these emissions, they are 100 to 360, now even higher actually, lower than those from the best equipment in the United States coal power plants. That they're all equipped either with electrostatic precipitators or baghouses at cadmium removal efficiency of about 98.8%. So that 1.2% that passes through in normal conditions from the coal power plants is at least 400 times. Now it's more than that, actually higher than the direct emissions of cadmium from cadmium telluride. So when you replace coal, obviously it's great. Now, energy payback times, as you know, energy payback is the time we measure typically in years that the plant, operating plant, it produces all the energy that it has been consumed in its life, or it's going to be consumed at the end of the life. It's still operating. You can see numbers there that they go down drastically because early on we had inefficient modules, very low efficiency modules, very thick layers, and a lot perhaps of cemented metals in the foundations. And now numbers for all technologies, depending on the solar irradiation, that's the biggest factor there, it can go down to a half a year under the very sunny areas, like 2400, the best areas actually in the southwest, the best areas in Australia perhaps. In Chile, up in Atacama, could be even higher, could be even less than that. But what intrigued us and made us actually going into this area not long ago, about 10 years ago, is what we saw a great divergence in the literature. A lot of studies that showing all the kinds of results. So we noted that there is divergence because people were using old data, could be 2000, 2005 actually publications that they were using 1990 data because there were actually some data from German systems that they were very well broadcasted those years, very detailed, and obviously they didn't actually reflect or represent the current technologies, and also different actually inconsistencies in methodology and treatment of intermittency. Some studies were assuming that you have 1-to-1 kilowatt-hour to kilowatt-hour actually use of batteries and so on. So we put together a task 12 under the auspices of the International Energy Agency that is still producing very good reports, and we in reports there we settle this issue by giving very concrete guidelines on the assumptions of what to be used, what not to be used, what is the power ratio to use and so on, and what should be included, what not to be included, and also we produce the reports with the CA data. And this task is going well with the co-actually management from UNSW and NRL now. Now, the evolution continues with established technologies. You can see here over the 5 years, from 2015 to 2020, a big reduction in the energy payback times of crystalline silicon. Why? For the most part, actually, is the reduction of the thickness and the reduction of the kerf loss, because we actually the industry transition in diamond cutting from multi-wire slurry cutting, and instead of having with every cut 145 micron loss, now we are 65 micron losses. Thinner wafers, I think 170 here versus 200, and also the higher efficiency, 17% to 20.5%. About 25% betterness in multicrystalline, but 45, this is the most impressive here, is with the cast on the Sochraski, actually silicon that is a very high demand type of silicon. As you can see here, again, the Sochraski, silicon and the wafer from Sochraski, there are those two colors, the dark brown and the yellow, and you can see here in 2020 that they have been reduced a lot, again, because of the kerf loss reduction, thickness reduction, wafer reduction, and this improvement of the efficiency. And you have some reductions in multicrystalline as well. Now, with new technologies like perovskites, the situation can be even better, because perovskites actually, especially with solution-based feedstocks, they don't use a lot of energy. And you can see here just a summary picture. I'm going to show a few more details because I know that several people are interested in perovskites and they are doing perovskite research. The top segment of those bars is the balance of system, so the inverter, transformer, the cables, the mounting and support system, and the bottom one is actually the panel. You can see perovskites here. There are 4 perovskite single junction and 3 perovskite tandem. They are better because they're using less energy per kilowatt hour than the conventional ones, silicon or thin films. Now, this is a little busy, but I wanted just to give you an idea of what are the technologies that we use. Actually, we use technologies that at that point, 2 years back, they were actually representing the highest efficiencies in perovskite in the lab. I certainly hear the replacement, as most of the studies consider FTO fluorine tin oxide instead of indium tin oxide, because they recognize that there is an issue with indium. Okay, so they try, and although it's a thicker layer for the transparent top conductor layer, they use FTO instead of ITO because of the indium, because of concern about the indium. With tandem, we have actually mixed cation here, Celsius and formamidinium, it's a little difficult to pronounce, formamidinium and cesium. That is what we use. Those are at that point where the kind of record tandem from NREL and Colorado groups. And what perhaps it's too much detail here, I'm going to go a little faster, but what we see here is that what differentiates between different technologies is electricity consumption. So for example, a very fast construction, a very fast production using the roll-to-roll gravure printing that is implemented by Energy Materials using systems that have been in photo-sensitive film printing by Kodak. They're using actually the same machines there that they have altered them for perovskites. Very fast throughput. It has the lowest energy, electricity actually demand, about 75 kilowatt hours per square meter. The ones that are based on spray coating, they use more. They are because they are slower. But again, there is a caveat there that this the spray coating numbers that are based on our scaling up of lab measurements by assuming different energy use factors. Having data on equipment and the times it takes in processing, so they are not real commercial data. These are commercial data here. So maybe the situation with spray coating can become better, we don't know. Also, what we see here though is that in tandem, the biggest energy use is on the silicon that is underneath, not on the perovskite. So that's the biggest one. Using the single crystalline silicon, about 77% of the electricity consumption is based on silicon. The pie diagram on the right is actually describing tandem-to-tandem perovskite. NREL recipes by Joe Barry and others there, and cool. So a lot less energy because they don't have the silicon. And obviously to make the panel, you have to add the encapsulation. So glass to glass has about 9%. And here you have a different functional unit. It's actually primary energy, megajoule per square meter. Before it was electricity only. Again, when you have tandem, perovskite to perovskite, you have less primary energy because you save the crystalline silicon. If you're using the glass and PET as the back sheet, you're using less energy than if you have glass. Okay. Now, all of this, the comparison so far assume perhaps the same longevity, the same life expectancy. But as you know, perovskites, they are not really tested for very long lives yet. I mean, we're talking about less than a year actually studies in the lab. So here we run energy payback or energy return on energy investment for different lives, 10 years, 20, and 30 years, and compare the 4 thin film perovskite and the 3 actually tandem with the conventional ones. And what we see for different grids, the current fossil fuel dominated grid and also a grid that will be mostly renewable energy, where you replace electricity with electricity. For a fossil fuel dominated grid, you replace actually primary energy from electricity, so you have higher benefits there because, again, electricity is at higher quality of its energy. So here, I draw a line that is at the level of silicon, 30 year, and you can see that single junction perovskites between 10 and 20 years, it could give you perhaps the same energy return on energy investment. The actual number is about 12 years. So if they last at least 12 years, they can give you the same energy return on energy investment based on this data with crystalline silicon that lasts 30 years. With multicrystalline using silicon at the bottom is closer to 20 years here. 20 years life, you have to have closer to 20 years life in order to have the same energy return on energy investment as crystalline silicon. Now, what else we should look at when we're talking about perovskite, especially talking about the lead halide perovskites, and all the industry actually records that I showed before on single junction. They're based on methyl ammonium lead iodide. And you know that it has lead, okay? So with lead, actually, there is an issue because lead is toxic. We haven't done, I think nobody has done actually fire testing of perovskites to see if lead is going to be retained there or not. Obviously, it depends a lot on encapsulation, but we don't have products there to test them. And the amount of lead actually is relatively low, maybe about 0.4 grams per square meter, versus cadmium in cadmium telluride is about 5 grams, and lead in lead solder in crystalline silicon is a little more than that. So it's a small amount, but nevertheless, but actually lead, the methyl ammonium lead iodide, when it degrades in the cations, MAI perhaps, and also lead iodide. Lead iodide is very, very, very soluble. We're talking about many orders of magnitude more soluble than lead from solder or cadmium from cadmium telluride. Many orders of magnitude more soluble. So there is an issue there. So we did a study just published, actually I have one PhD that I co-advised with Drexel University, and we did some screening analysis there, assuming that you have breakage of modules from 100 megawatt and 500 megawatt solar farms that use in perovskites, and you have that rain will take the lead down on the topsoil, and then from there it could go to water, groundwater, and so on. But it's interesting that we assume that it goes first into the soil. So what we found is that the soil actually, based on the screen analysis using again the EPA's soil partition coefficient module, the dilution attenuation factors going from soil to water, and a Gaussian plume dispersion, assuming that some dust can be airborne, but only from one centimeter of the depth, and it could be actually dispersed in there. Under these assumptions, we found that the water and air actually concentrations, they will be below the drinking water standards. But I don't call it this as the end of the story as highly deterministic, because again we have assumptions, we don't have data on SPLP on acidic leaching of lead iodide from soil, and of course it does not represent the pathway that it goes directly into water. What happens here in these studies is that the soil actually retains it. That's what we see. So more studies are needed on this. Now, remaining challenges and new opportunities. Photovoltaics end of life management, recycling, implementation. We need recycling. It's happening, actually is mandated in Europe, but although the levels that is mandated, they are not really high enough, but it's not mandated in any of the countries. We are working for this implementation for many years now in the US. I think that is going to happen. Dual use of land, I think, is a good solution wherever actually the land is such that it could maintain both agriculture and photovoltaics, and also ecosystem service from solar facilities. But what are the real issues, remaining real issues? The intermediacy, variability, those are real issues, okay? But there are also opportunities. And what are the opportunities? We have affordable, inexpensive, clean energy, a lot of it. A lot, maybe more than what we need in specific locations. What can we do with this? We can produce water, we can produce hydrogen, we can use it, right? And for this, actually, I started with this list from a Nobel laureate in chemistry, Dick Smalley. He got the Nobel in 1996 for his invention of fullerenes, and is considered in the US as a father of nanotechnology. He put, this is a list of declining priority. He put energy at the top because he assumes, and I concur, that if we have affordable, clean, abundant, and inexpensive energy, that you have solutions, at least partial solutions, for the water problem, food, environment, poverty, fewer wars in the Middle East, and so on. So we started really looking into water as well. For years, we were looking just energy and the environment. We started looking in my center, including water, into this spectrum of investigations about 5-6 years ago. And we looked into different solutions. But before going to the solutions, let me actually highlight here what is common between water, desalination, and also, as I mentioned before, production of hydrogen, because there is a lot of hydrogen now that is catalyzed. The production of hydrogen with electrolysis is also catalyzed because of the affordable solar energy, right? We have a lot of solar energy there. Both technologies, actually, when they're using fossil fuel, they produce a lot of carbon dioxide, and the cost of producing water and the cost of producing hydrogen from electrolysis is very, very, very dependent on the cost of energy. About 40 to 60% of the cost of producing water or producing hydrogen is the cost of energy. So what we have been doing at Columbia is looking into flexible designs and dynamic operation of both desalination and the hydrogen electrolysis plants, that they can handle some of the variability of solar. Also, we looked into inexpensive solar thermal designs that could use waste in addition to solar thermal, but I don't think I have time to talk about this, so I'm just going to give you two highlights. One on flexible desalination design that uses the most established desalination technology, reverse osmosis, and the most established solar energy, obviously cheaper, photovoltaics, and also solar hydrogen. We'll talk a little bit about photovoltaic powering electrolysis, but also the potential use of solar thermal and the waste thermal into desalination there. Just a few highlights. So a concept that we developed and actually implemented with all the mechanical parameters of it, and they took a prize actually in the competition between US and Israel on solar-based desalination is what we called active salinity control reverse osmosis, where we use different salinity levels of water. So having from waste water treatment, low salinity waters or brackish water, and combining with the high salinity water, seawater or industrial oil and gas water. So different pretreatment, but having in two different reservoirs and mixing them in a manner that follows the availability of energy. So when you have a lot of energy, then in the middle of the day, we're using more seawater. When you have less energy, when you have clouds and so on, or early during the day, or actually some hours at night when we have also energy storage, you use more of the low salinity water. And in this case, in those scenarios, the production of fresh water is maintained approximately the same, but you take in actually advantage of the different salinity, the variability of salinity that follows the availability of energy and or the prices of energy. Now, with water electrolysis, about the same story. There are two actually basic electrolyzer technologies, commercial ones, alkaline and PEM. PEM is actually the proton-based membrane technology. It's more flexible. It's typically operated at 1.7 ampere per square centimeter, and they have a Faraday efficiency of about 85%, but it could take higher current densities. Higher current density means more electrons and more hydrogen coming out, but at a penalty of efficiency. Okay, so the efficiency can be reduced. If, for example, you get to 6 ampere per square centimeter, the efficiency will be only down to 62% from 85%. But you get more hydrogen. So there is our studies, and this what we see here, it corresponds to the actual pricing in the California ISO during half our prices during a whole 18 months there. If you use actually those prices as a guide, and when it's low solar, low electricity price, you put more in electrons there, higher current density, the other way, the reverse, if the prices are high, we found a sweet actually spot at about 3 amperes per square centimeter for California. That's the lowest levelized cost of hydrogen. Now, this doesn't come as a free lunch, because when you have actually higher densities, you can have more damage, really. You have more degradation. And we model for that certain assumptions in terms of degradation. And you can see here some highlights of what really are the mechanisms typical for degradation when you work on higher current density. You can have low conductive oxides, you have some membrane thinning, you can have some actually hot spots, oxygen gas bubbles, large localized pressures, and you can have gas diffusion, really, and you can lose both hydrogen and oxygen, and you may create some risky conditions there. And the people are looking into strategies like a nanostructure and conductive oxides that can reduce the iridium loadings, protective platinum coatings, and bipolar plates, super hydrophilic surface treatment of titanium, the titanium element that prevent runaway voltages. There are some mitigation strategies, but those are not developed yet. There are companies, though, at least one company that I know, Nel Hydrogen, that is Netherlands-based, but it also has production facility in the US. They are trying to do that, and they say that they have actually, they have prototypes that work on a high current density, but we don't have a product out yet, not a commercial product out yet. So there will be some additional cost there, but based on the data we have, we feel that it's actually a good actually way to go. But even now, without this, without the new technology that can also use power electronics, that they are more suitable for high current densities, we can have dynamic operation of electrolyzers by using the current technologies and a modular function. The same way that actually the big solar farms work now, they have a lot of inverters and the central control unit for all the inverters, and by operating some inverters at a lower actually capacity, then they can handle the variability. If you have, typically actually, those are called utility-friendly solar farms, that they can operate at 10% less than total capacity, and they have a headroom to increase the capacity is needed, when it's needed. And they can also provide auxiliary services like frequency control and voltage control. The same way, modular operation of electrolyzers, because it's like batteries. You have many units, and you could keep some at partial capacity and others at full capacity, and you can take actually advantage of this. We know that projects that have been developed in the United States for wind and solar, they follow this principle with the current technology, but looking at the different sizing actually scenarios depending on the prices and depending on the resources. And they can be controlled with SCADA system architectures. Again, the typical control actually from a central unit that it could control the individual inverters based on a signal from the utility, based on a signal, in this case, from the demand. All the kinds of things that can happen with control devices in a power plant with many inverters. The same apply to in a plant of electrolysis with many electrolyzers. And also, and I discussed actually with somebody this morning, I think a PhD student in Greg's group, there is a potential for using solar or waste heat for desalination to take advantage of the lot of heat release when you dynamically operate electrolyzers. When electrolyzers, the PEM electrolyzers, operate at 1.7 ampere per square centimeter, they release about 7 kilowatt hours per kilo of hydrogen. But when they operate at higher current density, they are less efficient, so they waste more heat. This heat is enough, we found, with detailed simulations, to power a solar thermal type of technology of desalination. Again, thermal technology, like a low temperature multi-effect distillation at a lower cost than reverse osmosis. There is a lot more to show here, but my host is signing me that I think I should go into conclusions, so and leave time for Q&A. But I will be glad to give you a lot of details on each of these aspects, several papers on this. So I hope that actually I was convincing to you. You probably were convinced even before actually you heard this presentation. The PV industry evolves in all sustainability dimensions, right? It's good technology. It's better than other technologies. Renewables are much better than all the other technologies. But active dissemination of research results I think is essential to maintain the support of public and governments. So we should take the extra time that it takes for active dissemination of research results, okay? To show how good it is. Recycling is very important, and we need to actually have this implemented in all countries. But it can be optimized to help and make it profitable rather than hinder the affordability of PV systems. Low-cost solar creates new opportunities while addressing humanity's big problems, availability of water, okay? Also food and so on, having more into fertilizers. Solar variability challenge addressed with process hybridization. I just give you a few highlights there, but of course there is a lot of work behind those. Advanced modeling and controls offering flexibility and value-earning grid services. I haven't touched on that, but if you provide voltage and frequency control, you can ask really for much higher prices from the ISO. The gas speakers do that, and they operate only a few hours in the summer, but they get actually, they are paid, instead of paid 4 cents per kilowatt hour, they could pay 20 cents per kilowatt hour, 30 cents per kilowatt hour. But we don't have that actually marketed yet for solar farms, but they could provide frequency and voltage control. It has been tested, it has been validated, but we need the market. Okay, I think that's the end. Sorry.
Thank you very much, Vasilis. Really, a whole heap of really interesting stuff there. Thank you very much. We're sort of over time, but there's no critical problem with room availability or anything. There's nobody else coming in, so I think Vasilis would forgive you if you need to leave. But if you're interested and want to stay for a few questions, and if there are any questions, then I think we should go ahead and do that. So, are there any questions? All right, this gives me a great opportunity because I have a few. So the first one I noted, Vasilis, was you talked early in the slide set about floating PV and in places where land is in shorter supply than in our country and your country probably. This is a big issue. Have you looked at the lifetime of the modules in that environment? Because it's a tough environment, I think.
I haven't. So yeah, you could have more corrosion, but there can be also benefits there with reducing evaporation. But I think from what I've seen, perhaps anecdotally, is that we don't expect really a significant reduction in the life. I mean, if you have good encapsulation, again, I mean, you protect completely from moisture ingress. Moisture ingress anyway, I mean, let's say it won't be much worse than having modules in Florida where it's very, very high humidity, unless you immerse them in water. And there are some actually designs that they are perhaps they're thinking about some immersion to have additional cooling. Those perhaps could have a higher corrosion impact. Bottom line is that we don't expect, if they're well encapsulated, to have any additional corrosion effects, but we haven't done any studies. I don't know people that have done comparisons.
Thank you. I'm not going to bore you all night with my questions, so please.
Well, so you talked about the importance of disseminating research to the public. What have you found is the most effective way of doing that? Like, what has the most impact? It
is to do proactively, to anticipate questions even before they are asked. That's the best way. And we've done as much as we could early on. And actually, the Department of Energy was funding this research. We're looking into toxicology of new materials, elements, potential environmental safety impacts early on. But this doesn't stop, because the more it grows, the more photovoltaics become a major, actually, competitor to fossil interest. You expect that barrage of attacks to continue happening. I have been actually in hearings about that have to do in county councils with the new solar farms, and these questions come up, like it could pollute. Like, I mean, people don't want to look at the literature, but they say, oh, perhaps they could pollute, they could actually alter the ground and so on. So you have to be alert and really be there, giving the answers, but to the greatest extent, to the research before the questions are asked. Then you have less questions asked, at least not from the well-meaning people. The well-meaning people will be convinced, they will be looking at the literature, they will be convinced. But there are others that they're just actually guided from vested interest, and those could continue asking questions that we know that they kind of have answers already.
So I was wondering, in the future, do you think making renewables more sustainable, the challenges, is it mainly going to be technological or like government policy or something else? What do you see as the biggest challenge?
I don't think that we need government incentives any longer. I mean, what we had, they created a market, we helped a lot. I mean, the incentives, for example, in Germany, Japan, and then Germany, especially Germany, they helped really very, very, very much in creating the markets that then we all enjoy now. But now we have enough of this. I don't think we do. But of course, the government oversight is always important. Now, for recycling, perhaps, I mean, some people think that it have all to be voluntary, and it started in Europe as industry voluntarily actually program. It served the industry very well, so that was a proactive approach too. They anticipated that would be covered under the WEEE, the Waste Electronic Equipment actually regulation later. So they set the way that they want to do. The industry was proactive before the regulations. It was smart. Then they actually led the regulations the other way around. But I don't think that it was going to happen without expectation of regulation. And perhaps it has to be regulated to have this impact in other countries. But also we need to be smarter on separations and what we recover from recycling to make it profitable, or at least affordable.
Yeah. One last question.
Yeah, so you mentioned about the solar desalination for hydrogen production. So I feel like for hydrogen production, the water we require is pure. So the thing is, for PV RO configuration, the water produced by this kind of system is still needs some post treatment. And also, but for like solar thermal desalination, like using the multi-effect distillation, we can produce some like super pure water for hydrogen production. So the thing is there any like comparison for like economically or environmentally for comparing these two kind of solar desalination technology for hydrogen production?
Absolutely. I think this slide here, it shows the comparison. So you needed to demineralize the water, and the reverse osmosis single pass won't do it. You need triple pass or with ion exchange. That's why it's more expensive here. Okay, because you need to take down actually the salinity to below 50 ppm or 30 ppm. RO will give you 200, 230 ppm is not enough. So you need the triple pass or you need double pass and ion exchange. So that's why the cost is higher. Then the solar thermal though, if you're using the waste heat though, it depends. Because if you buy steam, it's about 2.5 cents per kilowatt hour. But if you have waste heat, it's free. I assigned a cent, 1 cent, because you need a heat exchanger, you need some system though. Then it's less expensive. The thermals actually energy is less expensive. The thermal desalination, that is the low temperature MED, 60 degrees, 70 degrees Celsius, multi-effect distillation, becomes less expensive than the reverse osmosis triple pass. And also there is another beauty here, that it can be autonomous system. You don't need grid. You don't need anything from the grid. It can be platforms in the middle of the sea where you produce hydrogen, and maybe you need a diesel to start it, but when it starts and keep producing waste heat, you can have an autonomous closed loop system that produces hydrogen in the middle of the sea or in a remote location. Okay? So it's better, as you said, it's better than reverse osmosis, although for conventional freshwater production, reverse osmosis from seawater is less expensive than MED from seawater or brackish water. But in this case, because you need an additional desalination, additional demineralization, then thermal becomes better.
Okay, thank you, Vasilis, and thank you, audience. But we'll draw to a close now. And if we just thank the speaker one last time.
Thank you.